if I take a comb and a piece of paper, and I brush my hair with the comb and then put it near the piece of paper, what is going to happen is that the comb is going to lift the piece of paper up. So what kind of a force that makes the comb lift the piece of paper, how they attract like that? And could we say that this force is the force of gravity between two objects of different masses? Actually, we cannot say that this is the force of gravity, because the force of gravity doesn't care if we comb our hair first or not. And if I take the comb and shake it like that, the piece of paper is going to fall down so easily. So we could think that this new force created between the comb and the piece of paper must be very weak, because it cannot overcome the force of gravity. But actually it would be very wrong to think that, because this new force is actually 10 to the power 42 stronger than the force of gravity. So what is this new force? And if the comb is pulling the piece of paper, so what is trying to pull the piece of paper down when we shake it? What is trying to pull the piece of paper down is the force of gravity. Here is the comb, and here's the piece of paper attracted to it, and the comb is lifting the piece of paper. Here's the entire planet, and when we shake the comb and the piece of paper falls down, it takes the entire planet so that it compensates for the force created between the comb and the piece of paper, and the piece of paper falls down. Professor Shankar from Yale, when he talked about this topic, he joked and said that he's the type of a person that would think that the entire world is against him, but actually this time he's right. If we take the comb and we shake it like that, the piece of paper falls down because it takes the entire planet to compensate for the force created between the comb and the piece of paper. So this new force that is created between the comb and the piece of paper must be very strong, because it takes the entire planet to compensate for this force between the comb and the piece of paper. It's an enormously strong force. The theory of electrostatics explains this comb and piece of paper incident and many other experiments. The formula that explains everything is called Coulomb's law. Coulomb's law says that certain entities have a property called charge. You have a charge or you don't have a charge, but if you have a charge, then your charge is measured in coulombs. If we have an entity that has a charge Q1 and another entity that has a charge Q2, they will exert a force on each other, that is, F is equal to Q1 Q2 4 by epsilon 1 over r squared, and r is the distance between the two entities. We could say that r is the distance between them, and when we say that, we would assume that these entities are like point charges, but we could consider that r, the distance, is the distance from the center to center, and this when we assume that they are objects of finite size. Actually, it doesn't matter so much. Now let's look at the number 1 over 4 by epsilon naught. Well, if we have a charge that is equal to 1 coulomb and another charge that is equal to 1 coulomb, and they are separated by only 1 meter, then the force that they exert on each other would be this number. It would be this number, which is equal to 9 times 10 to the power 9 Newton, which is an enormous force. Actually, we should write this formula more carefully because force is a vector, and we should say force on whom and due to what. Let's say that we have a charge Q1 that is at the origin and another charge Q2 who is sitting at a point whose position is the vector R. Then the force on 2 due to 1 is equal to Q1 Q2 4 by epsilon naught 1 over R squared. This is the magnitude of the force. We could suggest that the force is such that Q1 is pushing Q2 away. We want to make this into a vector. To make up a real vector, you take its magnitude and then you multiply this magnitude by a vector of unit length in the same direction. We could write the unit vector in many ways. We could write it as E of R. This is a standard name of a unit vector, a vector of length 1 and in the direction of R. We could also write it as R over R, where this R is the length of R, and this unit vector would be also parallel to the direction of R. We also know that the force on 1 due to 2 is equal to negative the force on 2 due to 1. Now, how do we get repulsion and how do we get attraction? The two charges that we have, if they have a positive sign, if it's a positive charge, then if we use the formula and we do the calculation, we will find that they repel each other. But if one of the charges has a negative sign and we use the same formula and we do the calculation, we would have a negative sign in front of the whole thing. So repulsion will be turned into attraction. So the charge Q could be of either sign. It could be a positive charge, it could be a negative charge, and it also could be 0. There are certain entities that do not have any electric charge, and if you put them next to a million coulombs, nothing happens. Now, getting back to the comb and the piece of paper. Now, if we have a plastic comb and we run it through our hair and then we put it next to a piece of paper, the piece of paper sticks to the comb, and that is because the charged comb now induces an opposite charge in the piece of paper, and as opposite charges attract, the paper sticks to the plastic comb.